All right, so let's have a look at these practice problems here. So number 3, we're going to start off with this. So you see that we are looking at points in three-dimensional space that are 3 units away from a line AB. Now, again, this is the kind of problem that will appeal to your intuition here. The idea is, if we look at this, it kind of makes sense here. If we have this, if we're 3 units away from this here, normally in 2 dimensions, it would just be sort of a line up here and a line down here as well. But because we're in 3-dimensional space, knows those lines sort of like rotate around. So essentially what's going to happen here is that your intuition will tell you that we're actually going to get a cylinder. So we're going to get something that looks like this here. So I'm going to draw in these things here. And we're going to get a cylinder that looks like this. So there's going to be a cylinder, a right circular cylinder here. And it makes sense here because if you look at the endpoints A and B, right, every point on the circular base of these cylinders here is going to be 3 units away from A or B, respectively, based on which side you're looking at here. So we're going to have a right circular cylinder like this. Now, of course, this is not the only case here, because note that this cylinder only stops here. But we also have points out here that are also 3 units away. So in a way, in addition to the cylinder here, we're also going to have, if you think about it here, we're also going to have what appears to be half a sphere. Because remember, we talked about how a sphere, every point in a sphere is a fixed distance away from a given thing in space. Given point. So essentially our solid looks something like this here. It's going to be almost like a sausage here. You have a right circular cylinder in the middle, and then there are 2 sort of hemispheres at the edge. So let's label what we know. The nice part about this is that this is a sphere with radius 3 here. Each of these are half spheres, so that's a full sphere there. So that means the volume. And then we also have this entire thing with a right circular cylinder. The height is x and the radius is 3. So we should be able to put this all together, therefore. So let's see. The sphere is going to be 4/3 pi times 3 squared, because that's the radius here. Oh, sorry, 3 cubed, my fault. And then we're going to add the volume of the cylinder. Now that's pi r squared h. That's pi times 3 squared times x, since we don't know the height of the cylinder here. And this altogether is going to be 216 pi. So now we have this sort of thing here. So the first thing we notice is that there's a pi and everything, so I can cancel the pi's out, and the pi's will just go away. And now we just calculate here. So that's a 3 cubed. 3 cubed times with the 4/3 here. This knocks out one factor of 3, leaving me 3 squared. So we have 3 squared is 9 times 4 is 36. So we have 3 squared is 9, so it's 9x equals 216. So therefore we can go ahead and put that in here. So we get 9x, looks like it's 180 here, and therefore the length of the segment, as you can see here, is 20. Pi r squared h, we have all this here, we can do that, okay? Let's move to number 4. So number 4 is a problem that I wrote for a middle school contest. You have a circular cone, again, height 8, radius 6, and it's held to the vertex at the bottom. The sphere is dropped in, and it's wedged into the inner surface of the cone, so that this sphere is now tangent to the inner surfaces here. So we want to find the distance from the vertex to this closest point in the sphere. In essence, we're looking at this distance down here. Now, we're told that the sphere has a radius of 2, so we can go ahead and set that up here. Here's the center of the sphere, and this is a radius of 2 here. So, what makes this problem difficult is the fact that we have this in 3D. Let's go ahead and try to convert this into a 2-dimensional problem here and see what we can come up with. So we can convert this into a 2-dimensional problem, and by just looking at it the right way, we can go ahead and set it up like this here. We're going to look at it head-on like this, like so. So this, everything here actually collapses very nicely here. Okay, so now this becomes, because there's a right circular cone, each of these slant heights are the same, so there's an isosceles triangle here. And in the inside here, we're going to have a circle, like so, okay? And again, we're trying to calculate this distance here. So I'm going to call it, so this triangle is going to have vertices A, B, and C here. I'm going to call the center of the sphere O. Now, in this situation here, we know we can figure everything out here, actually. I'm going to go ahead and extend this upward. Look at the height of the cone. The height of the cone is going to go up here and hit the center of the base. So I'm going to call that point D here. All right, so let's start filling things in. We know this is 6, and DA is 8 here. Now, this is a right triangle, so we know that since this is 6 and the height here is 8, therefore AC is 10 here, okay? Now, in this situation, since it's tangent, we know that tangents make right angles with circle radii. So we can go ahead and sketch this in here. I'm going to call this point here E, and we have this sort of thing here, so that's 2. and we have all these pieces here, so I'm going to call this point down here F. That's 2, that's 2, we have all this here. So now our triangle looks like this here, and in fact, if we take a look at this, I can actually look at this here. We see that we have, so we ignore triangle BAD at the A here, because ACD is sufficient. This is just a by symmetry. We can go ahead and set it up like this here, and go ahead and figure this out. We note that this triangle OEA here and CDA here happen to be both right triangles, and they both share angle A here. So we actually do get some similar triangles here, and that's going to be really helpful for us. So in fact, that gets us that CDA here should be similar to, in this case, CDA here is going to be similar to OEA. We can set it up like that, right? So now we can go ahead and fill this stuff in here. So we're going to try to redraw the triangles CDA and OEA so that we can, look at the triangles and try to set them up in the proper fashion here, and then set up a ratio and finish it up, right? So again, we got these two triangles here. Here's A, here's C, D, and here's O and E here. Oh, yes, O and E here, and here's A at the bottom. Okay, so we're going to have to fill in what we know. We know CD is 6, we know DA is 8, and we have CA here is 10. Now, the only thing that we know here is that OE is 2, which is really nice. So, in essence, what we see here, our goal is FA, and FA here, as you can see, is just, this OA minus 2. So all we need to do is figure out what OA is. Now, it's pretty clear here that based on this, we have a 3-to-1 ratio here. So that means everything's in a 3-to-1 ratio, so we can say 6 to 2 is 10 to OA here, right? And set it up like that. We get, so let's see, that's, in this case, that gets 6 OA equals 20. So OA here is 20 over 6, which in this case is 10/3. And now, because now OA is 10/3, so we have the 2 there, we now have FA, which is our goal, which is 10/3 minus 2, and that yields us a total of 4/3. And that's what we have there, okay? All right, now problem 5. Problem 5, we have a square pyramid here. There's a base, ABCD, and a height, vertex E. So we're told ABCD has an area of 196, and all this other stuff. We want to find the volume of the pyramid. Now, the problem cautions you that the pyramid is not a regular pyramid, not a right regular pyramid, and I think you can see this here. If E were indeed directly over the center of the base here, then all the triangular lateral faces would be exactly the same area. But we're told that ABE and CDE are completely different areas, so that's actually going to be a issue. In fact, what happens here is that because ABE has a greater area than DCE here, it means that the height is going to be slanted a little bit to the right. So E is actually going to be a little bit to the right of the center here. So what we have here is that, since we're trying to find the volume of the pyramid, remember the volume of the pyramid is 1/3 the area of the base times the height. Okay, now that's easy. They gave us the area of the base, which is 196, which actually tells us that each of the sides has length 14. This 14, this 14, this 14, this 14 here. So now the question is, what's the height of the pyramid? What is this perpendicular distance thingy here? What is that? We don't know that yet, unfortunately. So what we're going to have to do is try to figure out how this sort of thing works. Now, we're told that ABE and CDE has an area of 91, so that's particularly helpful here. In fact, let me go ahead and redraw this here. What we're going to do is now going to look at, we want the heights of these triangles here, because we can actually determine those, right? So the blue segments we can determine here. Now, if we switch our view, so now we're looking from the top down like so. It looks like this here. Here's A, B, C, D, E. Again, it's going to be a little bit off center here. E is going to be over here. And this is what we have. Again, this is A and C are not necessarily collinear here. In fact, it can't be collinear, but we are drawing a really bad we're not drawing a very 2-scale diagram here. So we're going to try to calculate each of these distances. Note that we can go ahead and do the same thing with all of this. So we know that ABE here is 105. So we're going to look at these slant heights here. So I'm going to call this height here H1. So we know that 105 is going to be 1/2 times H1 times the base, and that base we know is 14 because we know that this is a square of area 196. So we can go ahead and set that up here. So we have H1 is, so let's see, this is going to be 210 divided by 14 here. Now there's a 7 in both, right? So we can yank out a 7 from each of these to leave us 30 over 2, and that yields us 15 here. So this H1 is 15. And now we can do the same thing over here, H2. We can do a similar calculation here with CDE is 91 here. And again, 91 is 1/2 times H2 times the height times the base, which is 14. And we can set it up in this fashion here. we can set it up like so. So the nice part about this, again, we can yank out a 7 like this here. We can so we can yank out a 7 from here. We're left with the 2. This yanks out a 7, leaves a 14. 1/2 times 2 is just 1. So we get H2 is 14 here. So therefore, what we have here is something like this. So you have your 15, your 14, and this here. Now, you may be thinking this doesn't make any sense, and you're right. That's because the reason that this is not 14, this is 8, 15, this is 14 here is because E, remember, rises above like this. So now we're going to look at a specific cut. We now know this here. So if we draw this triangle like so, notice that we have this. Let me call the midpoints here. I'm going to call this here F and G. We're now going to look at triangle EFG here. So EFG, if I can pull it aside, looks something like this here. So here is EFG, here's E, here's G, here's F, and we know that this is 15, this is 14 here. Oh, I'm sorry, I messed up here. The calculations were a little off. This is 13 here, I apologize. So that's 13 here. So there's 13 over here, and therefore this on the bottom, FG, is 14 here. So now we can actually do this. We just have to figure out what the height is, and that's going to be this blue line, this green line like this here. We call this H. So in this situation here, if you happen to remember things from my math team class, you'll know what H is immediately. If not, we can calculate it very easily here. We know that, in this situation, let me call the two pieces here X and 14 minus X here. So we can set up two equations here. We end up with something like H squared plus X squared equals 225, and then we also have H squared plus, in this case, 14 minus X squared is 169. So in this situation here, now we can try to solve this. We can set this up here. So the H squareds cancel out, they're gone. And we're left with what appears to be X squared minus 14 minus X all squared is 225 minus 169. Well, let's see. That is 15 minus 9 is 6. Okay, subtract 1, so 11 minus 6 is, so let's see, 15 here. 1, 11, that's 1, so that goes away. So we get 56 here, okay? So now this is a single equation, single unknown. We can solve this here. So you get X squared minus, well, let's see, 14 squared is 196. This is all in parentheses. Minus 28X plus X squared is 56 here. So now this is a minus sign. We can go ahead and set that up here. X squared minus 196 plus 28X minus X squared equals 56. And then this goes away, these go away here. And the nice part, you get 28X is 56 plus 196 here. That's 56 plus 200, which is 256 minus 4 is 252 here. And then from there, we should be able to figure out what's going on in this situation here. We should be able to get, if I'm not mistaken here, we can set it up and get X is 9. And the nice part about this is that, therefore, this is 9, this is 9, this is 14 minus 9, which is 5. So we have a 9 and a 5 here, and therefore the common height we know is 12. So, by the way, in case you're, for those of you who are interested in sort of the math competition, sort of this thing here, this is a very commonly known triangle. You have a 13, 14, 15 triangle. The height to the base is actually going to be of length 12. So you have that nice little 4 consecutive numbers, 12, 13, 14, 15. Now we know the height, so we can go ahead and finish the problem here. And therefore the volume of the pyramid is 1/3 the area of the base times the height, which is 1/3 times 12, and the area of the base is 196. So this is going to be 4 times 196. Now let's see, that's 4 times 200, which is 800, but we're going to subtract 16. 800 minus 16 here, and that should give us the volume of 784.